What's up, music nerds? I'm back with Chapter 8 of Hermann Helmholtz On the Sensations of Tone. The link to the webbook that I'm reading from is in the description. You can find the entire text of the book there, as well as all of the apps that I'm going to show you in this video, so let's get to it! Chapter 8 on the beats of simple tones. Last chapter we learned that two simultaneous tones create combination tones in our ear, but that only happens for notes that are different enough in pitch. Something different happens when the pitches are close together. As long as several simple tones of a sufficient different pitch enter the ear together, the sensation due to each remains undisturbed in the ear, probably because entirely different bundles of nerve fibers are affected. But tones of the same or nearly the same pitch, which therefore affect the same nerve fibers, do not produce a sensation which is the sum of the two they would have separately excited, but new and peculiar phenomena arise which we term interference. Let's take a look at interference. This represents two of the same simple tone being played. The peaks and the troughs line up with each other, so their sum is curve 3. The peaks are twice as high, the troughs are twice as low. Since the intensity of sound is proportional to the square of the amplitude, we have consequently a tone not of twice, but of 4 times the loudness of either of the others. Now, what if the phase is altered? Well, if they line up like in figure 54 here, the tones will cancel each other out. And this app allows us to see kind of every place in between. A real-life example of this is a tuning fork. If you rotate the tuning fork near the ear, there are 4 positions, here, 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 which you will hear the tone very clearly, and 4 where it's inaudible. And those would be when the prongs are at 45-degree angles here, 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 here. But we never see 2 people playing a note on the violin and them just canceling each other out and hearing silence. And that's because of the upper partial tones. Here is a contraption with 2 polyphonic sirens. One on top, one on bottom. The one on the top can be turned. The whole thing can be turned using this crank here, so you can alter the phase. When you play 2 unison notes on the top and bottom, and the difference in phase is half the vibrational period, they cancel each other out. But we don't hear silence because the second partial tone is twice the period, so that partial is being reinforced, along with every other evenly numbered partial tone. So we don't hear silence. Instead, we hear a jump in octave, and the tone is weaker because all of the uneven partials are canceled out. So now that we understand the effects of the phase differences, Helmholtz is going to use this crank handle at the top to slightly alter the pitch of the top siren by turning it the same direction as the disc inside. He's making the pitch slightly flatter, and if he turns it in the opposite direction, he makes the pitch slightly sharper. And what Helmholtz hears when he does this is beats. If we think about it physically, by turning the handle 1 rotation, we're bringing it through the 4 positions where the tone was stronger and then weaker because of the phase difference. And that makes us hear 4 beats. 1 rotation in the opposite direction of the disc means that the upper siren is getting 4 more puffs than the lower siren. Hence, the number of beats in a given time is equal to the difference of the number of vibrations executed by the 2 tones in the same time. Let's listen. Here's 4 beats in 1 second. That's what Helmholtz would have heard if he turned the crank once per second. And the more beats, the further apart in pitch the 2 notes. Let's go crazy. Let's go 100 beats. That sounds like a fifth. Okay, this figure shows us graphically what's happening with the siren. The top, C, is divided into 18 parts, or 18 puffs on the siren, and D is divided into 20. So we can imagine that C, this top siren, we're cranking in the direction of the siren, so we're getting 2 less puffs. We only hear 2 puffs at the exact same time in positions 1, 3, and 5, and at positions 2 and 4, the puffs are entirely offset, so they weaken each other. This represents 2 beats, and of course 20 minus 18 is 2. Beats can be produced in any instrument, but Helmholtz cautions to be careful when counting the beats of instruments that have loud or strong upper partials, because the upper partials beat, and they beat with double, triple, quadruple, and so on the number of beats as the prime tone. The next question we look at is what happens to beats as they get faster and faster, and how many until we can't hear them anymore. Helmholtz disagrees with Thomas Young's hypothesis, which is that they gradually pass over into a combination tone, the first differential tone, 30 beats in a second being perceived as a tone of pitch number 30. But this does not agree with Helmholtz's summational tones and his assertion that differential tones exist external to the ear. So instead, Helmholtz makes an analogy of intermittent sensations in the eye. When you look at a really bright light and then look at something dark again, the bright spot lingers in your vision. Or if you spin a glow stick around in a circle fast enough, you'll perceive a glowing circle. Hence, the phenomena are quite analogous for ear and eye. When the alternation between irritation and rest is too fast, the alternation ceases to be felt, and the sensation becomes continuous and lasting. But it's not as simple as when you hear X number of beats, you stop being able to hear them and instead hear a continuous, lasting tone. It also has to do with the pitch difference of the interval. Because the same interval, a semitone, has more beats the higher on the scale we go. But Helmholtz says we can still hear those beats, even if we can't count them, up to 132 in a second. Let's try. This is 5.8 beats per second. I could count those. 7.78. Woo! I don't know. Do you agree with Helmholtz that up to 100 and... we didn't even hear 130, we heard 110, that you can hear those beats distinctly? I don't know that I buy it. Now on the flip side, each of these intervals has 33 beats, but the intervals get wider as we get lower in pitch, and Helmholtz says that it sounds freer from roughness. See if you agree. He attributes this to the dampening of Corti's organ of the ear and the sympathetic vibrations of the fibers around the pitch in question. And that brings us to the end of the chapter. If there was anything that you want to go back and read in more detail, Or if you want to train your ear on the beat keyboard, go to sensationsoftone.com. And I'll see you back here next week for Chapter 9. See you then. Bye.